I'm going to give you my opinion on how to avoid prematurely optimizing a data access strategy, so you can hit the sweet spot between acceptable performance and minimizing effort. It's not fancy, it's not hard, and it's pretty fast. I'm going to show you how to load SQL tables with enough test data to draw out the potential problems as you develop and test your data access strategy. No third-party tools, just a handful of queries. I'm keeping it simple. So imagine you're creating a new feature and it requires a new table in your SQL database. As you develop that feature, you probably create a handful of rows to test with, which is great because you have a way to make sure your queries return the right information. And the save operations actually persist the data. Now, most repositories and UI designs won't cause a problem with a couple hundred rows. It's not until the real users start to use the application and generate lots of data. The performance problems then come to light. And the solution might be as simple as adding an index or a filtering criteria. Or you may need to redesign the schema or change the amount of data that you get from the repository. The point is, find out if you have a problem early so you can minimize the amount of refactoring needed. To do this, you're going to need a reasonably large amount of data. How much is that? Well, that depends on what you expect to see in the table a year or two down the road. If you're making a contact management tool and you expect to have 10,000 users, it's probably reasonable to expect that they would each have 100 contacts. So maybe a total of a million contacts with 2 million addresses. That's not so many, but it's enough to help you spot problems. Now, most of us are not building applications that will need to scale to millions of users, so test data shouldn't be larger than what you expect to see before you're willing to refactor the code. Let's start by talking about what I call fake data and its benefits. Fake data is nonsensical. It's the situation where you would populate a first name field with a GUID. And it would be a pain to try to test a contact management program where all the names were GUIDs, but it would be perfectly fine to warn you that an application is fetching more data than it needs to. Are there CPU-intensive operations occurring in the middle of data access functions? Do queries run efficiently? What indexes are needed? Do you need a schema redesign to improve performance? All of these are very real and important questions, but you shouldn't care what the answer is because when you're developing that feature with test data, you only need to know that it works. That's what you care about. Does it work? If it's too slow, then you can investigate why. The test data serves as an alarm to tell you when it's time to invest in performance tuning. So let's take a look at generating some fake data in SQL. SQL loves set-based operations. I can insert a bunch of data into a table really fast if I have a table to select from. So to start this process, I need a table of integers from 1 to a really big number. So let's quickly look at how we can do this iteratively. I'm actually going to declare two variables, one that specifies how many rows to create and one to act as a counter. And I can simply create a loop and insert the value of the counter to give me a table of numbers. The problem is, this is really slow. If I run this, all right, finally. 2 minutes and 48 seconds to do those inserts, which is way too slow. So now let's try a set-based solution to this problem. I'm still going to loop until I've inserted enough rows, but instead of inserting one row at a time, I'm going to select against the existing rows in the table and double the counter for each iteration. So I start by seeding the table with the number 1, then every time I loop, I insert double the number of rows. So 1, 2, 4, 8, 16 until I reach the finish. When I run this, it is so much faster because SQL loves set-based operations. And there we go, done in 5 seconds. Let's say I have a table customer that I need to populate with data so I can test my application. And this table is going to have a customer ID that's a primary key. It's an identity, so it'll get generated on its own. And it has a first name field and a last name field. It's pretty straightforward and simple. Let's say I want to put 1 million customers into that table. What I can do is I can go ahead and create a select statement where I select all of the rows in my numbers table from 1 to 1 million. And in the first name field, I can convert that number, for the first row would be 1, into a varchar so that it can fit into a first name field. And so it'll just be 1 underscore first name. If I run this, And you can see that it has to create the numbers table in this case because I'm using table variables in this example. So in, what is this, 8 seconds? 10? Yeah, 10 seconds, we get 1,000,000 rows. And if we look at what that data looks like, you can see it's just the number 1 with a first name and the 1 with a last name. So this is kind of nonsensical data. It's fake. It doesn't mean anything, but it's definitely useful if we want to go ahead and try out an application, a repository, to see how well it returns information. If we need an index, or if our data access strategy is working appropriately. Sometimes the data you use needs to conform to certain standards. Maybe there are business rules that are required for the data to be loaded from the repository and for you to be able to use it and to test it. Perhaps you need a distribution of data to conform to more realistic standards. I actually have tables that I use for generating test data that I've culled from other public data sources. So I have a table of seed first name, and that includes a list of all the first names that I've encountered and a quantity so that I can apply a distribution frequency that would match a real life scenario. So these can be kind of useful to generate and populate a test table. All right, so let's look at a more realistic example where our data needs to conform to some specification. We're still going to have a customer table, and I've also added a customer address table where we've got line 1, city, state, and a postal code. And in this case, I'm trying to insert 500,000 customers, and I'm trying to insert 2 addresses for each customer. So I could define some variables here to annotate that. And the challenge is that we're going to leverage our numbers table and join against our table of first names and our table of last names. Now, I've only got about 250,000 first names and about 250,000 last names. So that's a problem if I want to insert 500,000, because I can't just do an inner join where I join the primary key for the first name table with the number that's in the numbers table, because what will happen is I'll only get around 250,000 results. The numbers for over the 250,000 won't meet the inner join criteria. So how do I get by this? Well, I'm going to have to leverage the modulus operator. In fact, this is really hard to describe, so let's take a look at a spreadsheet. All right, so I think this might help explain the situation. When the counter is equal to 1 and I do a modulus 5s, because maybe there's 5 rows in the table, I'm going to get back a 1. That's fine. But when we get here to 5, I do 5 modulus 5, there's no remainder. So the value is 0. I can't join against row 0 because there is no row 0. What I really want to do in this case is use a case statement. So instead of returning the actual modulus, I'll just return the number of rows that are in that table. In this case, it would be 5, and everything is hunky-dory. As soon as I get to 6, I do 6 modulus 5. Now it's a remainder of 1. So I go back and I'm going to join on the first row in that first names table. So that's the behavior that I'm trying to implement with that case statement. Let's go ahead and take a look at that. All right, so I'm going to go ahead and select from the numbers table, and I'm going to join to the seed first name table based off of that case statement, so that I'm always going to get a valid foreign key value. And so once I get this, I'll go ahead and be able to insert the 500,000 rows. When I run it, you can see it runs in about 2 seconds. So pretty good. Now let's take a look at the addresses part. So for the addresses, we're going to go back to that notion of set-based operations over iterative operations. And the big thing we're going to want to think about here is that instead of inserting 2 rows 500,000 times, 2 addresses for 500,000 customers, we're going to actually want to insert 500,000 addresses twice, because that's 2 set-based operations that will perform much better. So what I've done is I've actually created a loop, an address loop, and I've said I'm going to execute this twice. And here on the on the where clause of my select statement, I'm going to specify the address loop times the number of customers. So the first time we go through this, we're going to select all of the numbers where the address loop is 0 times the number of customers, 500,000, that'll be 0. So all the numbers greater than 0, and then all of the numbers less than 500,000, right? The address loop will be 0 plus 1 is 1 times the number of customers, 500,000. So we're going to do this 500,000 times the first time, but then we increment our loop to 2, and then we run through again, and we'll be doing the second 500,000. Obviously, we have fewer addresses than we do customers. I don't have 500,000 addresses, so I'm going to utilize that same case statement logic with a modulus to make sure that I'm getting a valid address ID to store in the customer name table. All right, so let's go ahead and run this thing and see how long it takes. 2, 3, 4. 4 seconds, and we're done. It's actually 500,000 in one row, but one of those is the count statement. So really pretty quick. 5 seconds, we have 500,000 customers with 1 million addresses. Explaining that script can feel a little bit cumbersome that first time through, but really it is a way to populate a parent and child relationship in a database schema. And so you can use that same pattern over and over. You don't need to recreate the logic, you just need to change the table names and the fields. And that's why it actually doesn't take that long to generate a bunch of test data for a set of SQL tables.